Torque. Just like there are rotational analogs for kinematics, there are rotational analogs for dynamics. Kinematics allowed us to solve for the motion of objects without caring why or how they moved. Dynamics showed how the application of forces causes motion, and this is summed up in Newton's 3 laws. These laws also apply to rotational motion, but will be in a slightly different format. Forces underlie translational dynamics. A new term related to force is the foundation of rotational motion. It is called torque. The wrench is about to turn the nut by a force applied at point A. Will the nut turn? The nut will turn in a clockwise direction. Recall that left and right have no meaning in rotational motion. This force causes motion from rest, which implies an acceleration, angular acceleration. What if a force was applied to the nut at point B? The nut is attached to a bolt that is stuck in the wall. Will the bolt rotate or move? No, it won't rotate or move at all. It makes sense that the nut won't move translationally, as the friction of the bolt and the wood holding it is providing an equal and opposite force. But it did rotate when a force was applied at point A. Assuming the same magnitude force was applied at points A and B, what is the difference between the two cases? Why is it not rotating now? The distance, r, between where the force was applied and the axis of rotation is an important factor. When the force was applied at the axis of rotation, in case B, the nut did not rotate. And the larger the value of r, the more torque is applied by the force. Here's an aerial view of a door. So here's the door, it's going to swing this way, right? Assuming all 3 of these forces have the same magnitude, which force will open the door the easiest? If the doorknob's over here, where do you push on a door so that it will open? You've probably known this since you first started walking. Force A gives the greatest angular acceleration. Pushing perpendicular to a line connecting the application of the force, here, to the axis of rotation, here, results in the greatest angular acceleration. In other words, a force applied at an angle of 90 degrees will give the most torque, also known as turning effect. However, pushing it at a 180-degree angle, like this, will give no torque and will not cause the door to open. Force B, at an approximately 45-degree angle, will open the door, but not as effectively as force A. This combination of force applied at a distance and an angle from the axis of rotation that causes the angular acceleration is called torque, which is represented by the Greek letter tau. I draw it like that. Torque is a vector. This equation, RF sine theta, gives you the magnitude of the torque. How much torque will there be? If the object rotates counterclockwise, like if this is a door and it's opening this way counterclockwise, that is a positive torque. Negative values of torque cause clockwise rotations. The sine theta portion of this equation takes into account that the closer the force is applied perpendicular to the line connected to the axis of rotation, the greater the torque. Therefore, the greater the angular acceleration. Theta is the angle between the applied force and the line connecting it to the axis of rotation, so this line here. Remember, sine theta has its maximum value of 1 when theta equals 90 degrees. So sine 0 is 0. So let's say you pushed this way. We could call that maybe a 180-degree angle or a 0-degree angle. Both this way or this way are not going to result in any torque. Whereas pushing this way or this way, 90-degree angle, would give you maximum torque. And this confirms what we saw with the door. When you push the door at a 90-degree angle, it opens more easily than at any other angle. Sine 90 gives the maximum torque for a given force at a given distance. This symbol, which you will see on the AP equation sheet, means that only the perpendicular component of the force is going to apply a torque. So here, if we have a door with a hinge and we apply a force here at an angle, only this component, the perpendicular component, is going to apply a force. So what is this component? Well, if we have theta here and the hypotenuse of this triangle is f, we could say sine theta is that component divided by the hypotenuse, SOHCAHTOA, right? So then that component is going to be f sine theta. So when we have r perpendicular f, we can replace that with r f sine theta, because this will take care of the fact that it's only this component, not this component, that's going to apply a torque. The units of torque are Newton meters. Note how this is similar to work and energy. And in those cases, we replaced Newton meters with joules. Remember, work is force times displacement. Force is in newtons, displacement is meters. So you might think, here we have meters and newtons again, so you might think those are similar. However, torque is a vector, and work and energy are scalars. So to emphasize this difference, torque is never expressed in terms of joules, even though when we do work, we do convert this into joules, these Newton meters. So they are not the same. Which of the following forces will apply a torque? A, B, or C? Only force C applies a torque to the wheel and will cause the wheel to rotate. R, F, and sine theta all have non-zero values. Force A is a force directed at the axis of rotation and will therefore not cause rotation. In this case, theta, the angle between this point and this line, is 180 degrees, and sine of 180 degrees is 0. Therefore, even though this force is applied at a distance r away, and with a force, sine theta is 0, therefore no torque here. Force B is a force that is acting at the axis of rotation and will not cause rotation, because in this case, if you apply the force right there, r is 0. Therefore, torque will also equal 0. Torque will be illustrated by 3 more examples: balancing masses, levers, and screwdriver handles. Here is a balance with 2 masses attached to it. Block A has a mass of 0.67 kilograms and is located 0.23 meters from the pivot point, which is this point right here, sometimes called the fulcrum, the axis of rotation, the pivot point, any of those work. Block B has a mass of 1.2 kilograms. Where should it be located so that the balance beam is perfectly horizontal and is not moving? So here's an image of a real-life experiment that you can do in your classroom. Is this a translational motion or a rotational motion problem? Here's an artistic hint. The 2 boys on the left represent mass A, and the 2 slightly larger boys on the right represent mass B. A side note, there are many connections between physics and art. This would be a good project to research. As with all dynamics problems, let's start with free body diagrams. But we'll take the points on the balance beam that the masses are attached to make our free body diagrams. We are examining the locations where the forces are being exerted on the balance beam itself. So we're going to draw a free body diagram for this location, that's point A, and for this location, that's point B. Note the signs. Mass A is trying to get the beam to rotate counterclockwise, so we will consider its torque positive, whereas mass B is pulling this way in the clockwise direction. So it's trying to get the balance beam to rotate in a clockwise direction, therefore its torque is B. Now, what are the forces? Well, the force due to this mass, it's a tension, right, in this string. It's due to the weight of the mass. So that's just mg, the weight of this mass. This force, the tension in this string, is just going to be the weight of this mass. And both of these forces are being exerted at a 90-degree angle to the balance beam. So we're going to use these equations to continue. We're going to continue on the next slide. We can actually use Newton's second law rotationally. We have F equals ma for translational motion, while the rotational analog is net torque equals I alpha. We haven't learned about I yet, but if we set rotational acceleration to 0, so this whole side of the equation becomes 0, we can solve this problem. In order for the beam to not rotationally accelerate, the sum of the torques applied to it must equal 0. So the torques will cancel out. So we have one torque that's positive, the other torque is negative. And remember, to turn a force into a torque, we need R and we need sine theta. So you have your force, you have your distance from the fulcrum or the pivot point, and we have our angle. Now our angle is 90 degrees for both, and that just becomes 1. So that's just 1. But you can see that we have our force, which is mg, times its distance from the fulcrum. So we simplify and we get 0.13 meters. You can see that if you have a larger mass, you have to move it closer to the pivot point to make up for that. Again, many elementary school students already know this. If you're on a seesaw and you have to balance several students on the other side, you would position yourself further from the fulcrum than they are in order to be able to balance them out. A remark attributed to Archimedes, "Give me a place to stand, and with a lever I will move the whole world," also applies to torque. See how Archimedes has set up the Earth so it's closer to the fulcrum of this mountain here, reducing the amount of force he needed to exert to move it. Of course, this is not true. This is a fanciful illustration. But you can see that because the Earth is so massive, you're going to have to put it really close to this fulcrum in order to use a lever to lift it up. Here's a view of a screwdriver from the top. We're looking at the handle here. So this is like the back of the handle, and the shank is going into the page. Like we wouldn't be able to see the screw right now. Assuming a constant force applied to both screwdrivers, so let's say we try to twist it this way, there's a force, and with the same force, I'll draw the same force on this one, which screwdriver is going to turn the screw easier? And would a longer shank help? Remember, the shank is the long, thin part that connects the handle to the screw. The force is applied perpendicular to the radius of the handle. The forces are the same. Since torque equals RF sine theta, the greater the radius, the greater the distance between where the force is applied and the axis of rotation, the greater the torque, and hence the greater the angular acceleration. Screwdriver A is more effective. The length of the shank does not matter, assuming it is perfectly rigid and does not bend or deform under the force. The wider the screwdriver handle, the easier it will be to use. Example 1. A student exerts a force of 60 newtons on a doorknob. What is the magnitude of the torque if the force applied is perpendicular to the door and the door is 85 centimeters wide? All right, so here we have our givens. The force is 60 newtons. R is 0.85 meters, right? We got to convert that from centimeters. And the angle is 90 degrees. So we're going to use our torque equation and plug in our numbers, and we get 51 Newton meters. Example 2. A student exerts a force of 60 newtons on a doorknob. What is the magnitude of the torque if the force is applied at a 45-degree angle to the face of the door and the door is 85 centimeters wide? Just like before, we have our givens. Instead of 90 degrees, we now have 45 degrees, and therefore our answer is 36 Newton meters. Before, it was 51, but by simply pushing at a 45-degree angle instead of perpendicularly, we have lost some of our torque due to that force. Example 3. A lug nut on a tire requires a tightening torque of 120 Newton meters. If the wrench is 50 centimeters long, what perpendicular force must be exerted by the mechanic? All right, so we have our givens here. We start with our torque equation. We're going to solve it for force, so we'll divide both sides by r sine theta. Now sine theta, because theta is 90 degrees, this just becomes 1. So we're going to divide both sides by r, giving us force equals torque divided by r. Then we just substitute in our givens and we get 240 newtons. Example 4. 2 students are on either end of a seesaw. One student is located 3 meters from the center support point and has a mass of 60 kilograms. The other student has a mass of 45 kilograms. Where should that student sit with reference to the center support point if there is to be no rotation of the seesaw? All right, so we have our givens here. I'm just going to draw a little picture. It's always nice to draw a picture. And we have 45 here. We have our fulcrum here. Do you see I've instinctually placed the 45 kilogram block further from the fulcrum so that it will be in balance? But let's mathematically figure out what this distance should be. So we have the sum of the torques equals 0. We want the torque, the clockwise torque, to be equal to the counterclockwise torque so that they're in balance, so that they cancel out. We want them to add up to 0 so that this will not rotationally accelerate. So we'll say this torque is positive, and remember the torque is the force times the distance from the fulcrum times sine theta. But both of these angles are going to be 90 degrees, so the sines are going to go away. They're just going to become 1. So we set them equal to each other, and remember this one's going to be positive, this one's negative, therefore you're going to move this one over to the other side. And remember the force is due to the weight of the blocks that are hanging, or the masses, or I guess the students actually. The human students, I did draw them as blocks, sorry. All right, the human students are exerting forces due to the fact that gravity is being exerted on them from Earth, so those forces are mg. And so the g's cancel, we solve for R2, and we see, yes, it is 4 meters. The lighter student will have to be further away from the fulcrum in order to be in balance.